Today's lesson is to do with permutation. In our last talk, we were introduced to the multiplication principle. Today, we shall extend those concepts in a variety of ways. This will give us the power to tackle many new problems. As usual, let's begin with a simple example. How many different two-letter words can be made using the letters A, B, C, D, and E, each letter being used only once? Let's make some words. A, B is one such word. B, A is another such word. C, D is another. E, E is another, and so on. Recall how we began learning about the multiplication principle. We needed a systematic way to list the words so that we didn't leave anything out. Let's do the same here. So the first letter can be an A followed by B, C, D, and E. That gives us 4 two-letter words starting with A. The first letter, however, could be a B followed by A, C, D, E. Or it could be a C followed by A, B, D, or E. It could have been a D followed by A, B, C, E. And the last choice would have been an E followed by A, B, C, or D. So we see that there are 5 choices for the first letter. Having picked that letter, there are now 4 choices left for the second letter. For instance, in the case of A, if we picked A as the first letter, we could have followed it up with B, C, D, or E. However, if we pick C as our first letter, we could have followed it up with A, B, D, or E. The important thing to note here is that no matter which letter we pick first, we still have 4 different choices for the second letter. And since there are 5 choices for the first letter, we totally have 5 into 4 equals 20 different ways in which we can make two-letter words. So this is very similar to the multiplication principle. We have 5 choices for the first letter, and with every such choice, we have 4 choices for the second letter. So the total number of choices, or the total number of words of 2 letters we can make is 5 times 4 equal to 20. Let's move on. We stick to the same 5 letters, but now we want different 3-letter words that can be made. So I can pick the first letter in 5 ways. Now, having picked the first letter, I have 4 letters left to pick my second letter. So there are 4 ways to pick the second letter. Having picked the first and the second letter, I now have 3 letters left to pick the third letter. Am I allowed to use the multiplication principle here? Yes, I am. Because any choice of the first letter can go with any choice of the second letter, and that pair can go with any choice of the third letter. For instance, A can go with BD, or A can go with BE, or C can go with AE, or C can go with AB. Of course, C could also go with BE, C could also go with BD. So you see, the multiplication principle is at work here, and the final answer is 5 times 4 times 3 equal to 60. What if each letter can be used repeatedly? Let's try to use the same strategy. Well, now the first letter has 5 choices as usual. About the second letter now. Well, I can use the earlier letter again. So now I still have 5 choices for the second letter and 5 choices for the third letter. And each choice for each letter can go with every choice of every other letter. So we now have 5 times 5 times 5 equal to 125 different ways which to write 3-letter words. So what are the new words that we have created when we allow letters to be repeated? Well, words like A, B, 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 C, D, and E, E. Basically words where letters are allowed to be repeated. Let's stick with this example. Now, how many different 5-letter words can be made? Each letter being used only once. Now it's easy. First letter has 5 choices. The second letter has 4 choices. Third letter has 3 choices. The fourth letter has 2 choices. The last letter has just 1 choice left. By the multiplication principle, the total number of 5-letter words where each letter is allowed to be used only once is 120. How about if each letter can be used repeatedly? Then let's put down our 5 dashes for the 5 choices. Now the first letter, as usual, has 5 choices. The second letter also has 5 choices. Why is that? Because I can use each letter repeatedly. Third letter also has 5 choices. Fourth letter also has 5 choices, and the fifth letter, surprise, also has 5 choices. Multiply out all these choices because every letter can be paired with every other letter. I can't stress that often enough. And we get 5 raised to 5 ways. So, let's see. What's an example of a word in this set that isn't in this set? Something like A, B, C, D, where letters are repeated. Or, of course, B, 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 or C, D, C, D, A. In all these words, at least some letter is repeated. Since the product 5 times 4 times 3 times 2 times 1 will occur often enough, we need a shorthand notation for this. That notation is the factorial. So, 5 times 4 times 3 times 2 times 1 is called 5 factorial. Written 5 exclamation mark or symbol like this. Similarly, n factorial, or any number n greater than 0, would be n times n minus 1 times n minus 2 all the way down to 1. It's also written with this notation. For completeness sake, we define 0 factorial equal to 1. What could this mean? It means if I have no letters, then the number of ways I can arrange those letters is 1. Does that really make sense? I leave that for you to decide. Okay, let's use a newfound knowledge on factorials to tackle a few problems. You have 7 different maths books and 4 different history books. Then how many different ways can you arrange the books on a shelf? Does it really matter whether some book is maths or history? No, I just want to arrange all the books on a shelf. So I have 11 total books. And I have 11 slots on the shelf. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I can pick any of the 11 books to be placed here. Having used that book, I of course can't use the same book again, so I have 10 choices for the second slot, 9 choices for the third slot, 8 for the fourth, and so on. Each such selection of books gives me a different arrangement of books. And each selection can go with every other selection. So I'm allowed to use the multiplication principle and multiply out all these numbers to get a very large number which I won't bother counting, but I have a shortcut way to write it. 11 factorial. So the answer of arranging 11 different books on a shelf is 11 factorial. It's important here that we count two different arrangements when even two of those books are switched around. That means an arrangement like A, B, C all the way to K and B, A, C all the way to K is considered different because at least two of the books have been moved around. Let's stay with this example for a while and see all the different types of questions that can come up. So we still have 7 different books of maths and 4 different books of history. Then how many ways can you arrange the books on a shelf if all the maths books have to be together and all the history books have to be together? So now we can't just say there are 11 factorial different ways to arrange them, because in these 11 factorial ways, in many of those ways, the maths and history books will be mixed up. All the maths books won't be together and all the history books won't be together. So we need to split up the problem into 2 problems. Let's arrange the 7 maths books. Seven maths books can be arranged, as we know, in 7 factorial ways. Then let's arrange the 4 history books. 4 history books can be arranged in 4 factorial. What we do with these numbers? Well, any arrangement of the maths books can go with any arrangement of the history books to give me a complete arrangement of the 11 books. So, by the multiplication principle, I have 7 factorial times 4 factorial ways in which I can arrange the 11 books such that the maths books are first and the history books are second, the way I've written it. However, the history books could have led, followed by the maths books. And here too, we have 4 factorial ways for the history, 7 factorial ways for the maths, and 4 factorial into 7 factorial ways totally, where the history books lead the maths books. Now these are the only 2 ways this can happen. So the final answer is 7 factorial into 4 factorial plus 4 factorial into 7 factorial, which is 2 times 7 factorial into 4 factorial. Let's stick with this example of 7 maths books and 4 history books and look at other restrictions on arranging these books on the shelf. So in this example, how many different ways can you arrange the books on the shelf if no 2 history books can be together? So here the restriction is on the history books. There must be at least 1 maths book between any 2 history books. That's what will make them apart. Since there's no real restriction on the maths books, I'll first arrange the 7 maths books. The 7 maths books, as you know, can be arranged in 7 factorial ways. Now with each of these 7 factorial ways, I'll try to figure out the number of ways I can slot in the history books so that no 2 of them are together. These 7 maths books occupy 7 spaces. The spaces between them are where the history books are allowed. For instance, I could put a history book here, or 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 here. That's 8 slots if you count them. 4 history books have to be put in these 8 slots. Anywhere I put the 4 history books will cause at least 1 maths book to be between them. For instance, if I put the history books here, H1, H2, H3 and H4, as you can see, there is 1 maths book in between these 2, there are 2 maths books between these 2, and there are 3 maths books between these 2.
So the history books are kept apart. What we have done is we have created 8 slots for the 4 history books to occupy. Let's see how we can count those number of ways. So we have 4 history books. The 4 dashes signify the choices for each of the slots. Now, the first history book has 8 slots to choose from. History book 1. Having placed history book 1, we now have 7 slots left for history book 2. History book 2. There's 6 slots left for history book 3 and 5 slots for history book 4. So totally, the number of ways the 4 history books can be placed in 8 slots by the multiplication principle is 8 times 7 times 6 times 5. Now, slotting in these 4 history books can be done with each of the 7 factorial ways in which the maths books were arranged. So, again by the multiplication principle, the total number of ways the 4 history books can be slotted in with 7 different maths books such that the history books are apart is 7 factorial into 8 into 7 into 6 into 5 ways. This is a very important example. I suggest you go over it a few times so it becomes part of your thinking process. Okay, let's see another situation. We have the same 7 maths books and the 4 history books, and how many different ways can you arrange the books on a shelf? If now all the history books must be together. Okay, the 4 history books must be together. So I will treat the 4 history books, H1, H2, H3 and H4 as one fact book. Then how many ways can I make such a fact book? I can make such a fact book where all 4 history books are together in 4 factorial ways. For instance, it could be H1, H3, H4, H2, H1, H2, H4, H3, and so on. You know those ways. There are 4 factorial ways in which these 4 books could be arranged to make one fact book. So now we have one fact history book and we have 7 maths books. So how many books do we have in total? We have 7 plus 1 equal to 8 books in all. And how many ways can I arrange 8 books? In 8 factorial ways. What's special about these 8 factorial ways? Well, in these 8 factorial ways, there's 7 maths book and there's 1 fact history book. By reducing the 4 history books to 1 fact book, I have ensured that the 4 books are always together, which was the demands of the question. So 8 factorial ways is the number of ways I can achieve it, where the 4 history books are treated as 1. However, in each of these 8 factorial ways, there are actually 4 factorial different ways I can create of making that fact book. So, by the multiplication principle, the total number of ways I want for this question is 4 factorial times 8 factorial. Okay, let's look at another restriction on these books. And how many different ways can you arrange the books on a shelf if the first and last books must be of mathematics? So out of these 11 books, the first book and the last book must be maths books. So that's the restriction. Let's put our dashes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The first book must be a maths book, which means I have 7 choices for this position. The last book should also be a maths book. which means having taken one maths book for the first position, I now have only 6 choices for this last position. What about the middle 9 positions? Well, I have 9 books and I have 9 slots, and there are no restrictions on what book can go where. Every book can go anywhere. So I have 9 factorial ways in which to arrange these 9 books in between the 2 end books. By the multiplication principle again, the total number of ways I can arrange the books so that the first book and the last book are maths books is 7 into 6 into 9 factorial. How about if I turn the question around and I say the first and last books must be history books? Then, following the same logic, I now know that for the first slot, I have only 4 choices, one of the 4 history books. For the last slot, I now have only 3 choices because I've used up one history book. And for the middle 9, I now have 9 factorial ways because there are no restrictions. So the number of ways in which I can arrange these 11 books on a shelf so that the first and the last book must be history books is 4 into 3 into 9 factorial. Okay. In the previous examples, we were looking at permutations of objects where all the objects were different. For instance, all the history books were different, all the letters were different. Now we look at permutations where some of the objects are identical. So permuting them among themselves will not give me new arrangements. Let's look at a simple example. How many different 4-letter arrangements of the letters A, B, and C are possible? So, which are the indistinguishable objects here? Well, there are 2 A's which are indistinguishable. Let me try to use some earlier knowledge. Since I don't know how to handle indistinguishable objects, I will make these 4 distinct letters. I'll make the 2 identical A's into different A's. I'll call them letters A1, A2, B, and C. Now I have a better grip on the problem. Now I actually have 4 distinct letters, A1, A2, B, and C. In how many ways can I arrange them? I know that. It's 4 factorial ways. Let's look at some of these arrangements. A2, C, A2, A1, B, A1, B, A2, C, A2, B, A1, C, B, A2, C, A1, B, A1, C, A2, and so on. So I've written these 4 factorial arrangements in pairs. What's special about the pairs? The arrangements are the same except that A1 and A2 have been flipped around. So if you look at these 2 arrangements, here it starts with A1, A2, BC, and then I flip it around to A2, A1, BC. Here it's A1, B, A2, C, and it's A2, B, A1, C. I'm just flipping around the A1 and A2s. Again here it's B, A2, C, A1, B, A1, C, A2. Again I flipped around A1 and A2. So my 4 factorial different ways can be paired up, where each pair is the same except that A1 and A2 have been flipped around. The positions of B and C have not been touched. Okay, this helps me now reduce it to the situation of indistinguishable objects. So A1, A2, BC and A2, A1, BC, I now make the A1 and A2 indistinguishable. I'll call them both A. So both these permutations reduce to AA, BC. Both these permutations reduce to AB, AC. And both these reduce to BA, CA. All I've done is I made A1 equal to A2 equal to A. Now they become indistinguishable letters. So what's happening? Every pair of permutations is reducing to one single permutation. I can't count it twice now. I can't count AABC twice. I can't count ABAC twice because the two A's are the same. So I have a situation where 4 factorial different permutations have been halved. And now these give me all the permutations of AABC, where the A and the A are indistinguishable. So the answer I'm looking for is 4 factorial halved, or 4 factorial divided by 2. So let's understand this method a bit more. I had to arrange all 4 letters in as many ways as I could. Unfortunately, 2 of the letters were identical. So I treated the 2 identical letters as different. I denoted them by A1 and A2. Now I knew how to do this problem. It was 4 factorial ways. Then I listed the ways and I noted the ways which would shrink into one way. So every time I permuted just the A1 and the A2 among themselves, all those ways would shrink to just one way because A1 and A2 would be treated as identical. And that led me to the solution. Okay, let's try to use this method here. How many different ways can be formed using all the letters of the word? A test. So here again, I have 6 letters, but 3 of them are identical or indistinguishable. So how many different ways do you think I'll be able to arrange them? As before, I'll treat the 3 T's as different. So the new problem I have is A, T1, T2, T, S and T3. I have 6 different letters and arranging them is easy. 6 factorial ways. The next step is to group these 6 factorial ways in an intelligent manner, which is keep the A, E and S positions fixed and just move around T1, T2 and T3. So that after I shrink T1, T2 and T3 to T, T and T, I get my one permutation for these 6 letters with T1, T2 and T3 the same. So let's look at how I'll group it. Let's say I go with A, E, T1, S, T2, T3. So I have to keep A, E same and permute the T's. Staying with A, E same. A, E still the same. Note that I'm just permuting the T's. In the slots occupied by the T's, the A, E and S are always staying the same place. Sorry, that's an E here. The last one. How did I know it was the last one? Okay, so what have I done? I've kept A, E and S fixed and I've moved around the T1, T2, T3. I urge you to try to see if there's any other way in which these 6 letters can be arranged where A, E and S occupy these 3 positions and the T1, T2, T3 are moved around. Now all these 6 will shrink to A, E, T, S, T, T in our final requirement. So you see that each of these 6 different permutations are going to shrink to one permutation. So the final answer is 6 factorial divided by 6. Now that's 6. I need to explain that 6. How do I get that quickly? Well, that's easy. What's being permuted? The T1, T2 and T3 are being permuted in place. And how many ways can I permute 3 letters in place? That answer is 3 factorial, which is equal to 6. So, The 6 in the denominator is actually 3 factorial. It's the number of ways those 3 repeated letters can be permuted among themselves. So my final answer is now 6 factorial divided by 3 factorial. Are you getting a hang of this kind of problem? Let's go over it again. I needed to arrange the letters of the word attest. There were 3 T's that were identical. So I made them different. I called them T1, T2, T3 and treated them as 3 different letters. Now I had 6 different letters. I could arrange them in 6 factorial ways. I looked at a grouping of those 6 factorial ways which gave me a grip on the problem. So I looked at a typical grouping A, E, T1, S, T2, T3. Then I decided to keep A, E and S in their fixed positions and move around the T1, T2, T3. I got 3 factorial ways in which I could move around T1, T2, T3 because there were 3 different letters. So all these 3 factorial ways would shrink to one way if the 3 T's were now considered identical. And that one way would be AET-STT. So all the 6 factorial ways would be grouped in bunches of 6 and each of those would shrink to 1. So clearly the total number of ways is 6 factorial divided by 6. That 6 of course is not some magic number. That 6 is acquired because the 3 repeated letters T1, T2 and T3 can among themselves be arranged in 3 factorial ways. So the final answer is 6 factorial divided by 3 factorial. Okay. Let's increase the complexity. In how many different ways can I arrange the letters of the word minimum? So let's count the letters. I have 3 N's. I have 2 I's. I have an N and a U. That makes 7 letters. So of course now I have to separate out the identical letters. So I'll make the 3 M's distinct, M1, M2, M3. I'll make the 2 I's distinct, I1, I2. And I'll keep my N and my U. These are 7 distinct letters. Okay. 7 distinct letters can be arranged in 7 factorial ways. Now, by our earlier experiences, the 3 M's among themselves, M1, M2, M3, can themselves be arranged in 3 factorial ways. M's, 3 factorial ways. The 2 I's can be arranged in 2 factorial ways. So the reduction in this case will be due to the 3 M's becoming identical M's and the 3 I's becoming, and the 2 I's becoming identical I's. So there will be 2 steps of reduction and the final answer we'll get is 7 factorial divided by 3 factorial and divided by 2 factorial. So let's just abstract this into a rule. So suppose I have n different objects and I split them up into n1 of one kind plus n2 of another kind plus all the way to nk of another kind. So basically these n objects, there are n1 objects which are identical, n2 other objects that are identical and nk other objects that are identical. So there are k distinct objects. The first object occurs n1 times, the second object occurs n2 times and so on, and the kth object occurs nk times, totaling to n. In how many different ways can I arrange these n objects? The answer is n factorial, and now I start dividing. 1 factorial, then 2 factorial, then 3 factorial, all the way to k. In our previous example, with the letters of the word minimum, N was 7, N1 was 3 for the N's, and N2 was 2 for the I's. Of course, N3 was 1 and N4 was 1 for the 1N and 1U. Okay. So, the total number of ways we could arrange the letters of the word minimum was 7 factorial over 3 factorial, 2 factorial, 1 factorial, 1 factorial. The 1 factorials don't count, they equal 1, which is equal to 7 factorial over 3 factorial, 2 factorial, as we had got previously. Okay, here's a mega word, Permutations. I'm sure all you guys who do yoga are familiar with this asana. Let's just count the number of letters and the number of repetitions of each letter. So Permutations has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. N is 15. How many A's? 1, 2, 3. 3 A's. 2 C's. 2 P's. 'Is that it? 2 S's. That's 3, 4, 5, 6, 7, 8, 9. So I need 6 letters which occur once. There's a P, there's an H, there's an I, there's an M, there's an O, and there's an N. Yep, we managed to count this. Not bad. Okay, so the total number of ways you can arrange the letters of the word Permutations is 15 factorial divided by 3 factorial, 2 factorial, 2 factorial, 2 factorial. Let's move on, where not only do we have repeated letters, that is identical letters, but we also have restrictions put on them. So, how many different words can be formed using all the letters of the word minimum if no 2 M's can be next to each other? So now, remember how we had done where no 2 history books could be next to each other? We had first arranged the maths books and then slotted in the history books between them. So let's try doing the same thing here. So let's first figure out the letters that aren't M. So those are 4 in number. I, N, I again, and U. 4 letters with 2 identical I's. In how many ways can I arrange these 4 letters? You just saw how to count that. That is 4 factorial divided by 2 factorial for the repeated I's. So, here are the 4 slots for the I, N, I, and U, and they can be arranged in 4 factorial divided by 2 factorial ways. Having arranged the I, N, I, and U in these 4 slots, I now have 5 positions in which I can slot my M's. These are the 5 positions which will ensure that the M's are kept apart, that no 2 are together. In how many ways can I put 3 M's into these 5 positions? So, the number of ways I can put 3 M's into 5 positions needs some work. I'll treat the M's as different. So that's M1, M2, M3. I'll treat them as different, count the number of ways, and then force them to be the same. Okay. So now that the M's are different and I need to put them into 5 positions, M1 could go into any of the 5 positions. M2 after that has to go into one of the 4 leftover positions, and M3 after that has to go into one of the 3 leftover positions. So the total number of ways M1, M2, M3 can occupy 5 positions is 5 into 4 into 3 ways. Now I'm going to shrink these M1, M2, M3s into identical M's. So they can be arranged in 3 factorial ways among themselves. So the number of ways is 5 into 4 into 3 divided by 3 factorial. Now by the multiplication principle, I need to multiply the first set of permutations by the second set of permutations. And my final answer is 4 factorial by 2 factorial, which was the number of ways I arranged the 4 letters, times 5 into 4 into 3 divided by 3 factorial, which is the number of ways I arranged the 3 M's in the 5 slots created by those 4 letters. And this is my final answer. It looks intimidating, but if you break it down, you can understand each part of it. By the way, this method of reducing M1, M2, M3 to 3 M's, that is 5 into 4 into 3 divided by 3 factorial, will occur very often henceforth. So please get a firm grip on it. Let's look at a slightly more complicated question. A code word can use a maximum of 2 symbols. How many different code words can you make if you have 40 symbols at your disposal? Fine, so I have 40 distinct objects of 40 different symbols. And to make a code word, I need to arrange a maximum of 2 of them. So I could make a code word out of 1 symbol. How many 1 symbol code words will there be? Let's write the 1. 1 symbol code words, well, there are 40 symbols, so there are 40 such words. How about 2 symbol code words? 2 symbol code words is picking 2 letters out of 40. Let me break up this into when the 2 letters are distinct and the 2 letters are identical. Let me count 1 first. So 1 is, how many ways can I arrange 2 symbols out of 40 symbols when the 2 symbols are distinct? That's easy. The first symbol has 40 choices, and having used that symbol, I have 39 choices for the next symbol. So 40 into 39 is the number of ways I can make 2 letter code words where both the letters are distinct. How about 2 letter code words where both the letters are identical? Well, both the letters are identical. So it's like AA or BB or CC. So I'm basically picking 1 letter and using it twice. So that's 40 ways. So now what's the total number of ways in which I can use symbols? To make a maximum of 2 symbol code words. So we add all 3 parts. The number of 1 symbol code words was 40, plus the number of 2 symbol code words was either 40 into 39 and 40 more. 40 into 39 is 1600 minus 40, that's 560. So the total is 1640. We have 1640 different code words that can be made given the conditions. The second part of the question is, suppose a code word cannot have letters repeating. Then how many code words can you make? Well, you've already done that. You can make 40 1 symbol code words and 40 into 39 2 symbol code words where the letters are distinct. You just drop the 40 code words where the 2 letters are repeating. Okay. Here's another kind of example. A jeep can accommodate 5 passengers, including the driver. So let's mark the 5 seats. Of course, the only important seat is the driver, so I'll mark this as the driver's seat. The other 4 seats are unimportant. Anyone can sit anywhere. In how many different ways can 5 friends seat themselves if only 2 of them know how to drive? Okay, so I better pick the driver first from among those 2. So the driver's seat has only 2 possibilities. 2 people who can drive. Now there are 4 seats left and there are 4 people, and it doesn't matter where any of them sit. Each arrangement has to be counted separately. So 4 people sitting in 4 seats is 4 factorial ways. So the total number of ways I can seat these 5 passengers with the restriction that only 2 of them know how to drive is 2 times 4 factorial. That was easy. Sticking to the same jeep, now there are 8 friends and 3 of them know how to drive. In how many ways can the jeep be loaded if it must not have a vacant seat? That means we have to fill it with 5 people out of these 8. So, like before, I have the driver's seat and 4 other seats. Now the driver's seat has 3 choices because 3 of them know how to drive. So I have 3 choices for the driver's seat. Now these 4 seats, there are 7 people left to seat. 1 person has already sat down in the driver's seat. So those 7 people have to occupy these 4 seats. The first seat, there are 7 choices. Now the next seat, there are 6 choices because 1 person is sitting there. The third seat, there are 5 choices. And the fourth seat, there are 4 choices. By the multiplication principle, therefore, the total number of ways I can arrange these people is 3 into 7 into 6 into 5 into 4. We have occupied all 5 seats. What if we were allowed to have empty seats? Well, the situation is now complicated because it depends on which seats are empty. If I leave seat 1 empty or seat 4 empty, the arrangement will be counted differently. So, here the situation is where I have to now decide the number of passengers that will be seated and also which seats will be left empty. We don't have the machinery to tackle this problem yet, but we will soon enough in the next lecture. You can surely go ahead and try it.